Hi, Stu Schwartz from MasterMathMentor.com. This is video AB36. The topic is area between curves, and it covers the AB manual, pages 209 and 210. Consider two functions f and g that are both continuous on the interval a to b. Also suppose that the graph of both functions are above the x-axis and f of x is greater than or equal to g of x. We would like to find the green shaded area between the two graphs. We do this by drawing a Riemann sum rectangle. It has base delta x and height f of x minus g of x. So the area of any such rectangle is the quantity f of x minus g of x times delta x. And as delta x goes to 0, our area between f and g can be expressed as the limit, as n approaches infinity, of the summation I equals 1 to n of f of x sub I minus g of x sub I, all multiplied by delta x. And we know this to be, by the fundamental theorem, the integral from a to b of f of x minus g of x dx. Whether both curves are above the x-axis, only one is above the x-axis, or neither are above the x-axis makes no difference. If both f and g are shifted vertically the same amount, the curve changes, but the area between them does not change, as shown by the two graphs. So the relative positioning of f and g relative to the x-axis is irrelevant. So we have our formulas for calculating the area between any two curves. We assume that the functions are continuous on an interval, and therefore the area between them can be expressed as the integral between a and b of the top function minus the bottom function dx, if x is between a and b. And if everything is expressed in terms of y, then the area is the integral from c to d of the right function minus the left function dy, where y is between c and d. We will now do a series of problems finding areas bounded by curves. Obviously, the calculator's ability to approximate definite integrals can be used. In some cases, we will show the integral and then use the fundamental theorem of calculus to calculate it, and in others, we will just set up the integral and then approximate its value using the calculator. Realize that the calculator will give you a decimal answer, but if the functions are relatively simple, usually lines and polynomials, you can change it to a fraction, getting the exact solution. And even if you have to use the fundamental theorem of calculus, the calculator can serve as a check for your work. The first problem asks for the area between the parabola y equals x squared plus x plus 2, the line y equals negative x, and the two lines x is equal to 0 and x is equal to 2. We graph the functions to be sure that the two curves do not intersect each other anywhere between x is equal to 0 and x is equal to 2. Our area will therefore be the integral from 0 to 2 of the top curve x squared plus x plus 2 minus the bottom curve negative x dx. We will do this one by the fundamental theorem and therefore write the expression as x squared plus 2x plus 2. And when we integrate, we get x cubed over 3 plus x squared plus 2x evaluated from 0 to 2, and therefore our area is exactly 32 thirds. Our second problem is to find the area between y equals 6 minus x squared and y is equal to x. In the first problem, we have two lines, x is equal to 0 and x is equal to 2, as our left and right borders. This problem does not give that, which means we have to find their points of intersection. Our first job is to set the two functions equal to each other. 6 minus x squared is equal to x. And bringing everything to one side, we get quantity x plus 3, quantity x minus 2 equals 0, and x is equal to negative 3, and x is equal to 2. So our setup for the area is the integral from negative 3 to 2 of 6 minus x squared minus x dx. On the AP Calculus test, if this problem appears in the section where you are allowed to use the calculator, then by all means use it. We do not have to show our work by the fundamental theorem of calculus. In this case, we will assume that you can use the calculator, and therefore our answer is 125/6. In problems 3 and 4, we are asked to find the area between curves where we have to find the points of intersection between the two curves. In number 3, we're asked to find the area between any two consecutive intersections of y equals sine x and y equals cosine x. We graph both functions close to the y-axis. To get the points of intersection, we set sine x equal to cosine x, and therefore sine x over cosine x, which is tangent of x, is equal to 1. And our solutions close to the y-axis is x equals pi over 4, and x is equal to negative 3 pi over 4. So our area is the integral from negative 3 pi over 4 to pi over 4 of cosine x minus sine x dx. We would like to get an exact answer for this problem, and the calculator will only be able to give us a decimal answer. So we will use the fundamental theorem and get, for the integration, sine x plus cosine x evaluated from negative 3 pi over 4 to pi over 4. And therefore our area is the square root of 2 over 2 plus the square root of 2 over 2 minus quantity negative square root of 2 over 2 minus the square root of 2 over 2. Everything becomes positive, and we are left with 2 square root of 2. We can confirm our answer by using the calculator and realize that we will get a decimal answer, which will be equal to 2 square root of 2. In number 4, we are asked to find the area between y equals 2x cubed minus x squared minus 14 and y is equal to 4x minus x squared. We graph the two functions and realize that there are 3 points of intersection, and the curve on top switches. So we realize we're going to need two integrals to calculate the area. We first need to get our points of intersection. So we set 2x to the third minus x squared minus 14x equal to 4x minus x squared. And that gives us 2x cubed minus 18x is equal to 0. Factoring, we get x quantity x minus 3, x plus 3 equals 0, and x is equal to 0, and x is equal to plus or minus 3. So our first integral will be the top blue curve minus the bottom red curve evaluated from negative 3 to 0. So we have the integral from negative 3 to 0 of 2x cubed minus x squared minus 14x minus quantity 4x minus x squared dx. The second integral is the red curve minus the blue curve, or the integral from 0 to 3 of 4x minus x squared minus quantity 2x to the third minus x squared minus 14x dx. When we do this, we choose for this problem to do it on the calculator. we could put y1 to be 2x to the third minus x squared minus 14x, and y2 to be 4x minus x squared. So when we integrate on our calculator, we could simply say FNINT of y1 minus y2, comma x, comma negative 3 to 0 for the first integral, and then reverse it for the second integral. Each area turns out to be exactly 40.5, and therefore the total area is 81. Number 5 asks to find the area of the region bounded by the curves y equals 12 minus x squared, y equals negative x, and y equals 4x. We graph them in colors with 12 minus x squared in blue, y equals negative x in red, and y equals 4x in green. When we say the region bounded by, using the colors usually makes it clear, as we like to have all three colors on all sides of the region. However, that is ambiguous. We see that region A has blue, green, and red on all sides. The same with region B, which encompasses a first and second quadrant area, and also quadrant C. So in this problem, we will find the total area bounded by the curves. And if you get a problem where there is a certain amount of ambiguity, then they will make it very clear to you which region is required. We take advantage of the fact that 12 minus x squared is always the curve on top. However, we need to find the places where these curves intersect. We start by setting the blue curve 12 minus x squared equal to the red curve negative x. And we get x plus 3, x minus 4 equals 0, getting x is equal to negative 3 and 4. We then set the blue curve equal to the green curve, 12 minus x squared equals 4x, and that gives us x plus 6, x minus 2 equals 0, and x is equal to negative 6 and 2. Finally, we set the green curve equal to the red curve, negative x is equal to 4x, and x is equal to 0. So our integral will be, first, the blue curve minus the green curve from negative 6 to 0. And then we look at the blue curve minus the red curve from 0 to 4. So our integral is negative 6 to 0 of 12 minus x squared minus 4x dx, plus the integral from 0 to 4 of 12 minus x squared minus negative x, which is plus x, dx. And our answer is 72 plus 104 over 3, which gives the final answer of 320 over 3. In number 6, we'd like to find the area between the curves y equals 2x squared, y equals 4x plus 6, x equals negative 2, and x is equal to 5. When we graph all four curves, we see that there are three distinct areas that we need to find. We again start off by finding the points of intersection. We set 2x squared equal to 4x plus 6, and that gives us 2 quantity x squared minus 2x minus 3 equals 0, factoring to 2 quantity x plus 1 quantity x minus 3 equals 0, and x is equal to negative 1 to 3. So our first integral is the red curve minus the blue curve, which is 2x squared minus 4x plus 6, and that becomes the integral from negative 2 to negative 1 of 2x squared minus 4x minus 6 dx. The second integral will be the blue curve minus the red curve, or 4x plus 6 minus 2x squared, integrating from -1 to 3. And then finally, we go back to the red minus blue, integral from 3 to 5 of 2x squared minus 4x minus 6 dx. We end up getting 14/3, and the two other integrals turn out to be the same, 64/3, and our final answer is 142/3. On number 7, you are asked to find the area between the curves x is equal to 3 minus y squared and x is equal to y plus 1. The first thing that should hit you is that these are x as functions of y. And if you're going to use the calculator, you're going to need to get these in the terms y as functions of x. We first solve for y, and luckily it is easy in both cases. For the quadratic, we get y is equal to plus or minus the square root of 3 minus x, and for the line we get y is equal to x minus 1. We now graph the curves, and there are 3 of them. Y equals the square root of 3 minus x in blue, y equals negative square root of 3 minus x in red, and y equals x minus 1 in green. Let's find where the curves intersect. We set our green line, x minus 1, equal to plus or minus the square root of 3 minus x. And when we square both sides, we realize that no matter whether we had used positive the square root of 3 minus x or negative square root of 3 minus x, the right side of our equation will still be 3 minus x. So solving the equation x minus 1 quantity squared equals 3 minus x gets us to x squared minus x minus 2 is equal to 0. And that factors into x plus 1, quantity x minus 2 is equal to 0, and x is equal to -1 and 2. We can see by the graph that our green line intersects the red curve at x is equal to -1, and the green line intersects the blue curve at x is equal to 2. We also need to find where the blue and red intersect, and we set them equal to each other. The square root of 3 minus x is equal to negative square root of 3 minus x, or 2 square root of 3 minus x equals 0, and x is equal to 3. So now we can come up with our integrals with respect to x using vertical rectangles. We have 2 integrals. First, the green is on top and the red is on the bottom. And at a certain point it switches to the blue on top and the red on the bottom. So our integral is from -1 to 2 of x minus 1 minus the quantity negative the square root of 3 minus x dx. And then the second integral runs from 2 to 3 of the square root of 3 minus x minus quantity negative square root of 3 minus x dx. We can simplify this a bit. We get the integral from -1 to 2 of x minus 1 plus the square root of 3 minus x dx plus 2, the integral from 2 to 3 of the square root of 3 minus x dx. And while we can do this with the calculator, we could also do it by the fundamental theorem, but it will involve the little u substitution. We choose to do it by the calculator, and we get the 2 integrals are 19/6 plus 4/3, and our final answer is 9/2. However, a lot of that work was wasted because we can do this problem with respect to y using horizontal rectangles. Recall our formula will be the integral of right minus left from the lowest value of y to the highest value of y. So we first set the functions x in terms of y equal to each other. 3 minus y squared is equal to y plus 1. And that factors into y plus 2, y minus 1 equals 0, and y equals negative 2 and 1. So therefore, our area will simply be the integral from negative 2 to 1 of 3 minus y squared minus quantity y plus 1 dy. And this problem can very easily be integrated, and our answer is 9/2. In this particular problem, there were two ways to get our answer: working with respect to x with vertical rectangles or with respect to y with horizontal rectangles. We were able to work the vertical rectangles because we could easily solve for y. A warning that you may not easily be able to solve for y or may not be able to solve for it at all, and you may be forced to use horizontal rectangles. This happens quite a bit on the AP exam when the testers want to test your knowledge of both vertical and horizontal rectangles. Take a look at this humorous cartoon. It reminds us that some of the simplest mathematics that you learned in grade school is nothing but calculus in disguise.